Stand up, feel your weight, the ground beneath your feet, the pressure on your soles, that sensation pressing upward. You think gravity is pulling you down. Everyone thinks that. It's what you learned in school. Gravity pulls. Objects fall because Earth's gravity pulls them toward the center. You're standing here because gravity pulls you down and the ground holds you up. Simple, obvious, completely wrong. Gravity isn't pulling you down. Nothing is pulling you down. The ground is pushing you up. And that push, that force you feel in your feet, that's not resisting gravity. That's creating the sensation you call weight. Gravity itself, you've never felt it. Not once. Not ever. This should completely restructure how you understand forces. Let's start with what you think you know. Newton said, objects with mass attract each other. The force depends on the masses and the distance between them. Earth has enormous mass, you have comparatively little mass. Earth pulls you, you pull Earth, but Earth is so massive that your pull is negligible. Earth's pull is significant. That's gravity. That's the force making things fall. That's what keeps you on the ground. This explanation works. It makes predictions. Those predictions match observations. For 300 years, this was good enough. Newton's law of gravitation explained planetary orbits, explained tides, explained why objects fall at the same rate regardless of mass. The mathematics was beautiful, the physics was clear, case closed, except there was a problem, a philosophical problem. How does gravity work? Earth pulls you. Fine. But how? What's the mechanism? You're not touching Earth's center. There's no rope, no physical connection. Yet somehow across empty space, Earth exerts a force on you. Action at a distance. Newton himself hated this. He couldn't explain it. He just described it mathematically. The force exists. It follows this equation. Don't ask how. Just calculate. That bothered people. It should have bothered them. Forces require mechanisms. Push something, you touch it. Pull something, you touch it. But gravity works through empty space. No contact, no medium. Just mysterious attraction. Something was missing. Some deeper explanation. Einstein found it. And it changed everything. Here's Einstein's insight. Gravity isn't a force. It never was. What we call gravity is the curvature of spacetime. Mass doesn't pull on other mass. Mass curves the spacetime around it. And objects move along the straightest possible path through that curved spacetime. No force, no pull, no mysterious action at a distance. Just geometry. Think about this carefully. Take away Earth. You're floating in empty space. No forces act on you. You move in a straight line at constant velocity. That's Newton's first law. Objects in motion stay in motion unless acted upon by a force. No force means straight line motion. Forever. Now put Earth back. Suddenly you accelerate toward Earth. Newton says, that's because Earth exerts a gravitational force on you. Einstein says no. Earth curves the space-time around it. The straight line through curved space-time points toward Earth's center. You're still moving in a straight line, the straightest possible path, but space-time is curved. So the straight path looks curved to someone far away. You're following the geometry. No force required. This sounds like semantics. Like Einstein is just redefining what force means. But it's not. The difference is profound, and you can feel it. Literally. When you're standing on the ground right now, you feel weight, pressure on your feet. You interpret this as gravity pulling you down and the ground holding you up. Two forces. Balanced. But that's wrong. There's only one force acting on you. The ground pushing up. That's it. That's the only force. Wait, if the ground is pushing up and nothing is pulling down, why aren't you accelerating upward? Because you are accelerating upward. Right now, constantly, the ground is accelerating you upward at 9.8 meters per second squared. That's what weight is, not gravity pulling down, the ground pushing up, accelerating you away from the natural path through curved space-time. Here's how to understand this. Imagine you're in an elevator. The elevator accelerates upward. What do you feel? Weight, pressure on your feet, the floor pushing up. Now imagine you're standing on Earth. What do you feel? The exact same thing. Weight, pressure on your feet, the floor pushing up. These sensations are identical because they're the same phenomenon. The ground accelerating you upward. But wait, the elevator is obviously accelerating. You can measure it. Earth's surface is not accelerating. It's stationary. How can the ground be accelerating you upward if it's not moving? Because acceleration isn't about motion. Acceleration is about changing your state of motion. And your natural state in curved spacetime is free fall, falling toward Earth's center. The ground prevents that. It deflects you from your natural path. That deflection is acceleration. Constant upward acceleration, 9.8 meters per second squared. Now think about free fall. Jump off a diving board. You're falling. What do you feel? Nothing. No weight. No force. You're weightless. Why? Because no forces act on you. Air resistance, yes, but ignore that for a moment. In a vacuum, falling, you'd feel absolutely nothing. No sensation of falling, no sense of motion, just floating. Weightlessness. But you're accelerating. Falling faster and faster. Shouldn't you feel that acceleration? No, because you're not accelerating in your own reference frame. You're at rest, following the natural path through curved spacetime. No forces, no acceleration, just natural motion. The astronaut floating in orbit? Same thing, free fall, falling toward Earth continuously, but moving sideways fast enough to keep missing. Orbital motion is just free fall with horizontal velocity. And in free fall you feel weightless, because you are weightless. No forces act on you, you're following the natural geometry. So here's the strange reversal. When you're standing on the ground feeling weight, that's when you're accelerating. The ground is pushing you upward, deflecting you from free fall. When you're falling, feeling weightless, that's when you're not accelerating. You're following the natural path. No forces, true inertial motion. This is the equivalence principle, the cornerstone of general relativity. There's no difference between standing in a gravitational field and accelerating in empty space. They're physically identical. An elevator accelerating upward in deep space creates the same sensation as standing on Earth. You can't tell the difference. There is no difference. And the reverse is also true. Floating in orbit around Earth feels identical to floating in empty space far from any mass. Both are free fall, both are weightless, both are force-free environments. The only difference is the curvature of spacetime. Near Earth, spacetime is curved. In empty space, it's flat. But locally, in your immediate vicinity, you can't tell. The physics is the same. Free fall is free fall. Now here's where it gets deeply strange. If free fall is the natural state, and standing requires constant upward acceleration, then what is down? You think down is toward Earth's center, the direction gravity pulls. But there is no pull. There's only the curvature of space-time, and the natural path through that curvature points toward Earth's center. That's not down, that's just the direction of the local geodesic, the straightest path through curved geometry. Down is a local concept. It's the direction opposite the acceleration you're experiencing. When you stand on Earth, the ground accelerates you upward. So down is the direction you'd go if the ground stopped pushing. That's toward Earth's center. But it's not because gravity pulls that way. It's because space-time curvature makes the natural path point that way. And the natural path is what you follow when no forces act on you. On the other side of Earth, someone else is also being accelerated upward by the ground beneath their feet. Their up is opposite your up. Their down is opposite your down. But both of you are being accelerated away from the center. Both of you feel weight because the ground pushes you away from the natural inward falling path. There's no universal down, only local opposites to local accelerations. At Earth's center, if you could be there, there would be no down. The curvature is symmetric. The natural path doesn't point in any particular direction. You'd be weightless. No acceleration, no forces, even though you're surrounded by Earth's mass. Because the mass is all around you. The curvature cancels. The natural path is to stay put. No motion, no weight. Now think about orbiting, the International Space Station. Astronauts floating. They're falling continuously toward Earth. But they're also moving sideways, fast, about 28,000 kilometers per hour. So as they fall toward Earth, Earth's surface curves away beneath them. They keep missing. That's orbit. Continuous free fall, never landing. Those astronauts feel no weight, not because there's no gravity. Space-time is curved. They're in a gravitational field, but they're following the natural path through that field. Free fall. No forces, no acceleration in their frame. Weightless. If you could remove Earth suddenly, the astronauts would continue in a straight line. They'd fly off tangent to the orbit. But Earth is there, curving space-time. So the straight line through curved spacetime is a circle, or more accurately, an ellipse. The astronauts are moving in a straight line through curved geometry. That's why they don't need to fire thrusters to stay in orbit. They're coasting, following the natural path, like a ball rolling along a curved surface. No force pushing it along the curve, just the geometry of the surface determining the path. Now come back to you standing on the ground. You're not following the natural path. The natural path points down into Earth, but Earth's surface is in the way. The ground is solid. Electrons in the ground repel electrons in your feet. Electromagnetic force. Enormous. The ground pushes up, hard, accelerating you upward at 9.8 meters per second squared, constantly. You don't notice the acceleration because you're not speeding up. Your velocity isn't increasing, you're staying at the same height. How is that acceleration? Because acceleration doesn't mean changing velocity in the everyday sense. It means changing your state of motion relative to inertial frames. And the inertial frame is free fall. When you prevent free fall, you're accelerating, even if you're not moving. Think of it this way. Imagine space-time as a flowing river. The flow represents curvature. Objects in the flow move with it. That's free fall, natural motion, no forces. Now imagine you grab a rock in the riverbed. You're holding yourself stationary relative to the shore, but the water is flowing. You feel the pressure of the water pushing against you. That pressure is force. You're resisting the natural flow, accelerating relative to the flow. That's what the ground does. It holds you stationary in the flowing geometry of curved space-time. And you feel the force, the pressure, the weight, but there's no pulling. The river isn't pulling you downstream, it's flowing, and you're resisting that flow. The ground is resisting space-time's curvature, pushing you out of the natural free-fall path, creating the sensation of weight. Now let's talk about what you never feel, gravity itself. In Newton's picture, gravity is a force pulling you down. You should feel it, but you don't. You feel the ground pushing up. That's not gravity. That's the electromagnetic force preventing your atoms from overlapping with Earth's atoms. The sensation of weight is not gravity. It's the prevention of gravity's natural effect. When you jump for that brief moment in the air, what do you feel? Before you land, weightlessness, no force, no sensation. That's as close as you get to feeling gravity. And what you feel is nothing, because gravity isn't a force, it's geometry. And you're following it, naturally, no force required. Skydivers experience this for longer. Free fall, before the parachute opens. They're falling, accelerating toward Earth, from the ground's perspective. But from their perspective, floating, weightless, no sensation of falling, just wind resistance. But in a vacuum, perfect free fall, they'd feel nothing, no indication they were falling, just floating in space. This is why dropping things feels different from throwing them. When you drop something, it follows the natural path. When you throw it, you add velocity, changes trajectory. But once it leaves your hand, both the dropped and the thrown object are in free fall, following curved space-time, no forces, just geometry. Here's a thought experiment. You're in a windowless room. The room accelerates upward at 9.8 meters per second squared. You feel weight. Now the acceleration stops. You become weightless. Float around. Now the room is placed on Earth's surface. You feel weight again. Can you tell if the room is on Earth or accelerating in space? No. The sensation is identical. The physics is identical. This is what Einstein realized. Gravity and acceleration are the same thing. But wait, if gravity is just acceleration, why do things fall together? If you drop a hammer and a feather in a vacuum, they land at the same time. Same acceleration. How can the ground be accelerating both of them upward at the same rate? Because the ground is accelerating upward. Period. Not relative to the objects. Relative to the natural free-fall path. The hammer and feather were both in free fall, following the same geodesic. When they hit the ground accelerates both of them away from that geodesic. Same acceleration, same rate. In Newton's picture, this is weird. Gravity pulls them both down with the same acceleration despite different masses. Requires gravitational mass to equal inertial mass. Exactly. For no explained reason. In Einstein's picture, it's obvious. They're both following the same natural path. Mass doesn't matter. The path is determined by the curvature, not by the object's properties. So everything follows the same path, falls at the same rate, because they're not being pulled. They're coasting along geometry. Now think about tides. The moon doesn't pull the oceans toward it. Not exactly. It curves space-time. The near side of Earth is in slightly more curved space-time than the far side. Different geodesics, different natural paths. This difference creates tidal stress. Stretching, not pulling. The geometry on the near side points slightly more toward the moon. The geometry on the far side points slightly less. The difference pulls Earth apart, stretches it. That's tidal force, geometry gradients, not attraction. Black holes take this to the extreme. Near a black hole, space-time is so severely curved that all geodesics point inward. All natural paths lead to the center. There's no path that leads away, not even for light. Light follows geodesics too. Near a black hole, those geodesics curve inward, so light falls in, not because the black hole pulls it, because there's no outward path. The geometry forbids it. And inside the event horizon, space-time is curved so severely that the inward direction becomes time. You can't avoid moving toward the singularity any more than you can avoid moving forward in time. It's not that you're being pulled, it's that inward is the only direction time points. Moving away would be moving backward in time, impossible. This is what gravity is. Not a force, not a pull, geometry. The curvature of space-time caused by mass and energy. Objects move along geodesics, the straightest path through that curvature. When nothing interferes, that's free fall, natural motion, weightless, force-free. When something interferes, like the ground beneath your feet, you feel force, the force preventing free fall, pushing you away from the natural path. So when you stand on the ground, you're not being held up against gravity's pull. You're being deflected from your natural trajectory. The ground exerts force, upward, accelerating you, and you feel that as weight. But gravity, you don't feel gravity. Gravity is the absence of force, the natural motion, the path you'd follow if nothing stopped you. People falling from airplanes don't feel gravity pulling them down. They feel weightless, because they're in free fall, following the natural path. No forces. People standing on the ground feel weight, because the ground pushes them, prevents free fall, exerts force. This reversal is total. What you thought was the effect of gravity, weight, is actually the prevention of gravity's natural effect. What you thought was resisting gravity, the ground holding you up, is actually the source of the force you feel. Gravity doesn't pull, the ground pushes. And that push is what you've been calling weight your entire life. Now ask yourself, if you've never felt gravity, what is it? It's not a sensation, it's not a force you experience, it's the structure of space-time, the geometry, the curvature. It determines what paths are natural, what motion is inertial, where objects go when no forces act. That's gravity, not a pull, a geometry. And that geometry is invisible, intangible. You can't feel it directly, you only feel deviations from it. The ground pushing you away from the natural path. That's what weight is, not gravity, the prevention of gravity. So stand up, feel your weight, the pressure on your feet, the ground pushing upward. That's not gravity, that's the electromagnetic force. Electrons repelling electrons, the ground accelerating you constantly upward, away from the natural freefall path. That sensation you've called weight your entire life, that's not gravity pulling you down, that's the ground pushing you up. And gravity, you've never felt it, you never will. Because gravity isn't a force, it's the geometry of space-time. And geometry doesn't push or pull, it just is. The universe isn't holding you down, it's letting you be, following the natural path. And the ground is what's fighting, pushing, accelerating, creating the sensation you mistake for being pulled. But there's no pull, never was, just push, just geometry, just the ground refusing to let you follow the path space-time wants you to take. Gravity doesn't pull you down, the ground pushes you up. And everything you thought you knew about falling, standing, and weight was backwards. That's general relativity. That's Einstein's revolution. That's the truth about gravity. Not a force, a geometry. And the sensation of weight. That's you being deflected from the natural path. Constantly. Every moment you stand. Accelerated upward by the ground beneath your feet. Fighting against the flow of curved space-time. Welcome to the real universe. Where down is up. Where falling is rest. Where weight is acceleration. Where gravity doesn't pull. It never did.